Okay. In the early days, like, to my knowledge, I guess, basically the only way to make data visualizations with a scripting language was with matplotlib. And I think matplotlib is based on like MATLAB plots or something. Right, so this stuff's just been around forever. MathWorks, yeah. And basically this is what a Python one will look like. Wow, that's small. So this is pretty similar. I wasn't sure how to think about pandas. Pandas is really a data science thing, right? So it's not really classical scientific computing, but it's probably what you should be using to visualize any data. I found a scientific computing example we did in it. I feel like I kind of have to teach you pandas. But the other libraries this term, and we're going to do after that. So SciPy is like, you take NumPy and you add more equations to it. SymPy is, you take NumPy and you add algebra to it, so the variables can become symbolic. Scikit-learn is you take SciPy and you add machine learning to it. And Numba is you take NumPy and you make it go faster. So pandas is kind of this like thing that like doesn't fit in that well, but I felt like I had to teach it. So I'm going to teach you a little bit of pandas, and I think it'll be useful, and I think we have a good organizing example. But really the scientific computing class classically is the NumPy class, and so you do NumPy and then you do all the things that come off of NumPy, right? So we'll go ahead and do that. Okay, with that, without further ado, we'll get into NumPy. Slides, internet, all that stuff working for you okay?
Yes.
Cool. We'll do like a short sprint here and then take a break for coffee and then go from there. Right. My plan is to probably like drive down to Taco Bell at noon because I don't know where else to get lunch.
Taco Bell?
Yeah, is that okay for you?
Yeah, it's fine.
Yeah, it is the best I could come up with. So you're invited on that, and then we'll come back and finish up the afternoon, and I'll prop the door and call security if we have to. I think the one thing we should really do is either one of us should leave and one of us should stay in here, or we should plan on leaving as few times as possible to get back in. Okay, so what is NumPy? Fairly straightforward. It stands for numerical Python. You may know a variety of other programming languages. One of the classical things that goes on in programming languages is, hey, do you have lists which can have a different length, or do you have arrays which have a fixed length? And usually arrays also have one other thing, which is everything in the array has to be the same. A lot of times when Python is introduced, the list is used as the array type. And you just say, well, just don't change the size of this and don't put anything in this other than the type of things that are supposed to be in it. So we claim, for example, and we'll go ahead and open Python here. Will we? Yes, we will. Okay. So we make this claim that isn't really true, that this thing is an array. And it could be an array, but it's still fundamentally a list. And the thing that makes it a list is you don't really want to be able to do this. That causes it to not have all of the nice features arrays have, where you really don't want to be able to accidentally or on purpose change the type of one of the elements. And so what came around, right, is in the more scientific programming languages, which I think the real ones at the time were like Fortran, right? So people were just writing very low-level code. They did have an actual array type where that wasn't allowed. And so some people wrote something called NumPy, numerical Python. And NumPy has an array type. And can I just turn R? Right? And what this did is, well, these things are all floating point numbers now, whereas from R, the first one, that's an integer, and we can confirm it's an integer, right? Whereas in NP array of R, which we'll call, I don't know, num, the type of num 0, that's a float, and it's a special NumPy type of float, right? They're all floats. So this idea is meant to solve the problem that lists had in Python, which is that they were easy to work with for humans, but hard to work with for computers. And so if you're trying to do something hard on a computer, you can just take another minute and write slightly better code and get higher performance. And then the other thing arrays can do is we can say array plus equal 6, and we can add things to the end of the array. There's not really a graceful way to do that. I guess I don't even know what it would be. Would that work? Yeah, so that's something different, right? And so NumPy sort of responds to this problem that there were people that wanted to use Python to do things that computers were good at, but one of the things that made Python so great and popular is it was good at being like human-centered and friendly, right? So we actually needed to be a little less friendly and a little more powerful, and numerical Python's the answer to that problem. The basis of Python, or the basis of numerical Python, is the n-dimensional array object. Why do we call them n-dimensional arrays? Well, say we have a number, like pi, right, or 7. We think of that as a n-dimensional array of dimensionality 0, right? We say that's a scalar, that's just some value, right? Then say we have some vector, right? And a vector is probably the most common thing to have. I often think of vectors as, so for example, right now we're some number of miles south and some number of miles west from Atlanta, right? So we can say our distance from Atlanta is this, like sort of two combinations in the coordinate system, right? And we also often do that on the globe, distance from where the prime meridian intersects the equator, right? We say, oh, we're some distance in these 2 dimensions away. Right, so vectors are used quite often. Vectors are often also used in statistics to capture the measurements of an experiment, right? So if I have a variety of substances and I raise all of them to boiling point and write down all of their boiling points, that's a vector, right? That goes up one more level than to matrices, and the matrix is quite useful. And this is, the common example is I have some experiment where, for example, I am trying to synthesize some chemical, and I am making changes to the temperature at which the synthesis occurs, and perhaps the measurements, or the ratios in which I'm combining the reagents, right? So I put reagents on ratio on one axis, and I put temperature on the other axis, and then I have some kind of yield at each one of these intersecting points. So that's a matrix, right? Those are what was classically used as n-dimensional arrays. The next dimensional array is now called a tensor, and it's used in machine learning, and that's a matrix of matrices. I'm not going to touch on tensors this term. I think that's sort of a linear algebra topic, but NumPy can handle them just fine, right? There's no number of dimensions that NumPy stops working at. When you start working with vectors, vectors are historically governed by something called the vector calculus, where if we take the vector 1, 2, 3 and multiply it by 4, we're supposed to get 4, 8, 12. That's not what happens with Python. By default, if I take my Python array and I multiply this by 3, I just get 3 of the arrays. So Python lists are not doing vector operations, right? And we as scientists will frequently want to do vector operations, and especially will want to do vector operations if we're into machine learning, right? And then Python, or NumPy is pretty good at integrating with C, C++, and Fortran. It has especially a good library to interact with Fortran. I wasn't planning on teaching you Fortran, but I want you to be aware of this. If you're ever doing a calculation and you're annoyed how slow it is, the reason it's slow is because it's not written in either C or Fortran, right? So if something's slow, that's why. You can see this a little bit where float 64, that is, usually I think of that as a C language type. Really, it's a type in the physical hardware, right? But we're getting a lot more C-like in our NumPy, right? These fixed length arrays and so on. All of that is very C. It has linear algebra, Fourier transforms, and random number capabilities. The best example of this is actually just that it has pi in it. So it has a lot of mathematical concepts that aren't built into the base language, right? So if I just type pi in Python, I don't get anything, but after I have NumPy in, I can use that. So this is what NumPy says they do, and they're not wrong. That's pretty cool. Okay. The lists we were using in the income tax example, those already should have been 1- and 2-dimensional arrays. And there's a few things that make them 1- and 2-dimensional arrays, but here, we can look at my solution to intercepts.py. All right. This isn't too exciting, but what's going on here? Well,
Did you change the layout? Because now it's cutting me in the screen.
Oh, no, this one's cutting for all of us, I'm sure.
Oh.
But the bottom didn't matter. That's why I didn't worry about it. But you can also just copy it if you want. Let's exit here. Let's end Vim. So that's what it showed. But I can see it with Control minus. Oh, the other thing, I might as well show you this. I don't know if I've shown you this yet. Whenever things are cut, and maybe I should fix that, I wasn't worried about it. You can see the whole thing here. So, let's look at what we've got here, right? Well, first of all, this array is of a fixed length. No one is going to be adding additional tax brackets, right? This isn't as if we've taken some measurements and we might take more measurements in the future, right? This stuff has been set in stone. It's unchanging. Even if the cutoffs for the brackets change, it's unlikely an additional bracket will be added, right? Another thing that's going on, this is 2-dimensional. This is a excuse me. The problem with eating toast for breakfast is it's like very dry and crumbly. Jeez. Okay. Each of the elements of the outer dimension is also of length 2. So, for example, in Python, it is allowed to have something that we can. This is not an array. We can have 1, 2, 3, 4, 5. And if we look at this, this doesn't work as a 2-dimensional array because there's a different number of elements in 1, 2, and 3, 4, 5, which means we're fundamentally not measuring the same thing. It is a list of lists, and that's a reasonable thing to have. But if we're using lists to hold n-dimensional arrays, well, we're going to have to keep checking their n-dimensional arrays all the time. And I think import numpy as np.nd array of not an r. I think this is not allowed. Yeah. And if I put in a 1 here, is that okay? No, that's fine. Why is it doing that? Oh, there we go. Right. So the shape is wrong. It's not the shape of a 2-dimensional array. But the shape of this thing is the shape of a 2-dimensional array, which we can see. Take taxes. Let's take a look at it. It prints out differently in Python than how I styled it. But if we could say np array of taxes, we get back basically the same thing we put in. The only real changes here are that they're all floating point numbers. Something to point out is that these are integers and these are not integers, right? So that's going to be a little bit confusing. I was going to store the percentages as integers, but there's also a 39.6%, so it wasn't really up to me. There's no way to make 39.6 an integer. So what are we going to do now? We're going to change our existing lists, and we're now going to think of them as n-dimensional arrays, and we're going to change them into NumPy arrays. We're going to show some of the benefits of doing this. We're going to show some things that are easier, Maybe you will find some things are harder, and that's fine, but it's not my goal to demonstrate they're harder. It's my goal to demonstrate they're easier, right? And then after we do that, we'll just demonstrate some of the other NumPy features that are useful to know, that I think you would be expected to know. Ooh, 6, what's that? Okay. Is there an empty? I think there's an empty line right there. Hard to say. Okay. So, before we go any further, we have to introduce package management. Package management is commonly a feature of sort of the scripting languages like Python, and perhaps the most famous one is NPM, the Node Package Manager for Node.js. We are going to use the Python package index, and we're going to use pip to install NumPy. By default, your computer will not necessarily have Python on it, or, well, didn't necessarily have Python on it, but also won't necessarily have NumPy on it. So we're going to use Python to install NumPy. This is a little bit different than how I installed Firefox or OBS or Python, right? In that it's part of something I already have installed. So we're going to install it using this package manager that came bundled with Python. So we'll step through that process. In general, I use pip to install my Python packages. There are other tools that people use. The two most common are Conda and UV. You are welcome to use these. I'm not recommending either of them. A lot of people recommend UV, so I should let you know about that. But pip is a command line utility, and you don't have to take my word for it. You can just type pip at the command line and see what happens, right? A lot of people don't like pip. It has a lot of problems with it, and I've never really experienced and encountered those problems, so I don't have any personal animosity towards it. But you will find many recommendations to use something other than pip. For example, if we just look up how NumPy recommends itself to be installed, we come in here, it will recommend UV PixI before it recommends pip, and it will also recommend Conda before pip. My impression is that all of those are worse than pip, but that's okay. And this is what I had to do on my Linux device. I installed via apt, right? Which stands for like Advanced Package Tracker or something. So, how are we going to do this? Well, I am going to use Python. I'm going to specify the -m flag, and then I'm going to run pip. So I'm providing m as a flag to Python and pip as an argument to Python. I'm providing install as an argument to pip and NumPy as an argument to install, basically. Let's type all of that in and see what happens. Python, I'm typing Python 3, m, pip, install, NumPy. And that didn't take too long for me because I've already had it installed, but it might take a moment for you. When the install is done, I run Python, I import NumPy as np, and then I type print pren np dot underscore underscore version underscore underscore close paren. What's all of this doing? Well, I have an old version of NumPy over here. I'm on 1.26 on this computer instead of 2.01. Okay. The joke is always that scientists hate typing. That's what they say, right? And when we import NumPy, you remember when we imported the piecewise function, right? You can import it under any name, and so n is probably taken. You know, that's an arbitrary integer. P is already taken. That's probability, right? So, but we can take n and p, smush them together, and then we can say numpy just as np, right? So that's what the first line does. And you don't have to believe me, you can type np into your command, and you'll see, oh, np is referring to NumPy, right? You know what print does, and you know what np is. np underscore underscore version underscore underscore. Those two underscores, this is called a dunder for double underscore. This is just something that you're not meant to use in code. So we're not really supposed to add a value to version. np dot version +7. Yeah, I guess it's stored as a string, right? So we're not really supposed to fiddle around with that. It's just basically something that only exists for us to take a look at it like this. And so it has this special denotation with the double underscores to denote that it's supposed to be some sort of special kind of value, right? And we see there's other double underscores, and the most obvious one is the init.py. Init.py is the Python file that sets up NumPy when you import it, right? So there's double underscores all around. Now, we have introduced import previously, and so I have a pointer back to the NeoVim slides on that if you are interested. I can just open this quickly, and we can see. Oh, that's interesting. Okay, I'll have to fix that. That's a link to my personal device. Okay. Okay. Up next, we have arrays. Okay, so the basis of NumPy is essentially the array, and so we're going to be working with arrays here. The first thing to do in NumPy is to make an array. Arrays don't have to only contain numbers. I wouldn't bother putting something other than numbers in them, and basically the only thing I would decide is whether I'm going to put in whole numbers or decimal numbers, right? You also are going to want to use an array anytime you're going to want to do the same thing to a bunch of different numbers. So if you have a bunch of temperatures you're trying to translate from Celsius to Fahrenheit, or vice versa, right, you would often do that on an array. So how do we do that? Let's take our list of lists. We'll take taxes. I'm going to put taxes into Python here. I'm going to verify that I have taxes. There we go. We should examine taxes a little bit so we can look at the 0th element of taxes. That's the house on the corner, right? It's the first thing we see in taxes. And we notice that the house on the corner itself is perhaps an apartment building or a building with 2 lots, so we can look at the first sort of the 2 units we see in the apartment complex on the corner and see it's 9275. And then there is also a 0.1 in the same lot. The next house down the street also has a little building on it that is 0.15, right? So that's sort of what I'm envisioning here. This is perhaps a street of duplexes or something like that. So I have my list of lists. This is what it looks like. Oh, we should check the type. So taxes is of type list, and then taxes 0 is of type list, because it is a list of lists. Oops, I have to say type, not types. And taxes 000, or 00 is an integer. Unfortunately, taxes 01 is a float, so those are not the same type, so this is not a well-formed multidimensional array. Right? If we squint at it a little bit and say, well, they're both numbers, but really we shouldn't be doing that. So we have a list of numbers. They're not necessarily integers or floats. So NumPy is going to figure out a way to solve this for us, and what they're going to do is they're going to change all the whole numbers. They're going to put decimal points on the end of them. That is going to incur some performance and accuracy costs, but can't really do anything about that. So here is the information we have. Sometimes, and I don't know how much things like Excel and other spreadsheets are still used now, n-dimensional arrays are sometimes referred to as a substitute for spreadsheets. This is more common with the pandas data frame, right? But you have some column headers you have some columnar data, and then you have rows. And a row represents an observation, and a column represents a type of data. So I'm driving down the street, and I see that, oh, that house cost $9,275 and is taxed at a rate of 10% or something, right? So this is just a table representation of the n-dimensional array. Now, going back and forth here, notice we cut this off. This doesn't go all the way to the highest rate. This stops at 33%, right? But there's also a 35% and 39.6% tax bracket, but those aren't representable in an n-dimensional array. There are 5 cutoffs and 6 percentages, unless we count one of the cutoffs as 0 or infinity, both of which are odd things to do. So you cannot put this into a NumPy array, right? I expect whenever you're doing any scientific computing application, whenever you're doing anything in NumPy, you're doing machine learning, if you're doing data analysis, whatever you're doing, you're going to find a lot of things that are not quite arrays. When I was looking for example data for this class, I found a lot of things that weren't quite arrays, where they say, oh, this is an array, except these 3 examples where we don't have all the measurements. And it's like, well, then that's not an array, right? You have to decide what to do with that data, and then, to me, that becomes pandas very quickly instead of NumPy. But we've also seen a few ways to deal with this already. The income tax example is not an n-dimensional array, but we have converted it to an n-dimensional array. And how have we done that? Well, let's just talk about the way NumPy recommends visualizing arrays. And they like talking about grids. So I drew this out in a grid. This is lifted directly from the NumPy documentation. But we have here, I just took the first 4 income cutoffs, right? I put them in boxes. Perhaps we can visualize this again using the street analogy or not. But this is a one-dimensional array. It looks like a list, okay? Here's our sort of two-dimensional array. I used all 3 of the things we calculated. So this is an income cutoff. This is a marginal tax rate. And this is a discount, right? So people making fewer than this amount pay this much per dollar and get this much back. People making this amount pay this much per dollar and get this much off on their taxes. People making this much or more pay this much per dollar and get this much back, and so on, right? So this is a two-dimensional array, and we think of it as a grid. Now, you'd probably occur to you it's going to be really difficult to draw a 3-dimensional array because I only have 2 dimensions I'm working with here. So I'm not going to draw a 3-dimensional array, but it's sort of the same idea. And the 3rd dimension to this array would be single, married filing jointly, married filing separately, head of household. We would just have an array of arrays, right? In general, NumPy likes to represent this as, oh, perhaps you have a list of tables, or perhaps you have a table of tables, or perhaps you have a table of tables, right? And that's how you get to 6 dimensions, right? So in NumPy, they use n-dimensional arrays. They are arrays of an arbitrary number of dimensions, and oftentimes we're going to use 1, 2, or 3 of them, right? Uncommon to use more than 3, in my experience. They call it the n-dimensional array because they're using the same thing for all of these dimensions, right? So let's go ahead and use np array to make an np array. And it's going to look like this. We'll go ahead and show that. R equals np dot array of taxes. R equals np dot array of taxes. R. There we go. There we have it. This does look quite a bit different from taxes. One of the things you might notice right away is that NumPy elects to sort of print these out in sort of the same way I did, where you're printing each entry on its own row. This may confusingly look to you like these numbers are going up and down due to the changes in powers. So we're going to introduce scientific notation here. Are you familiar with scientific notation?
Yes, yeah.
Okay, I'll just go over it, and there's no reason not to go over it. So, oftentimes, in real life, when I'm dealing with numbers, it's like pick up n of something at the grocery store, and n is always between 0 and 9, right? Single-digit numbers. Sometimes we'll have n players on a sports team, and that's never more than 20 or something, right? I think the largest football teams might have 40 people on them, but they're not all playing at the same time, right? These things are also all integers. You can't have a non-integer number of football players. It's hard to have a non-integer number of oranges. People will say, oh, I ate half an orange, but I don't know. That means there's one orange that's been eaten, right? What this means is that human language sort of developed around not having the types of numbers that are used in science, because in science, gravity is 9.8 meters per second squared, and you can't really have 9.8 peaches, right? So there had to be other ways to express these values. And then another thing that happened quite early on in science is I think people realized there was widely divergent sizes of things, right? So most humans in either kilograms or pounds weigh 2 or 3 digits of information, right? But if we compare the weight of an ant to even the weight of an elephant, which are already not animals that are that different in size, they're both animals I can see, they're animals I can touch, right? Already, suddenly I'm comparing something that is less than a gram to something that is more than 1,000 kilograms, right? And so people don't tend to do well with these things, right? So if I say, how big is the difference between 1,000 and 1,000.1? It seems like that 0.1 doesn't matter, but in fact that's the entire weight of an ant, which is something that does matter, right? So scientific notation is sort of the way around this. And the way it works is it works oftentimes very aggressively in base 10. So we express numbers not as a single number that we say, like 1,150, right? We express them as how far they are removed from their most common multiple of 10. So 1,150 would be 1.15, and then it is 1,000, so it is 10 to the third. So we have a number representing the bigness and a number representing sort of accuracy. My impression is oftentimes, especially in like physics and astronomy, we're estimating something like the number of stars in a galaxy. You don't even have you just estimate how many orders of magnitude they call them as. So we say there's either a trillion or a quintillion stars in that galaxy. And like, what do you mean? Do I mean 1, 2, or 3 quintillion? I mean about a quintillion, right? You know, within several quintillion of 1 quintillion, right? And so that's sort of a different way of thinking about numbers. NumPy sort of preserves this, expecting the people using NumPy to be familiar with that way of thinking about numbers. So what are the rules here? B is any integer, and A is not required to be an integer, but is required to be in between 1 and 10. If it is either 1 or 10, you're supposed to use 1. So I say 1 less than or equal to A less than 10. A is permitted to be positive or negative. So its magnitude is between 1 and 10, but it can be also between -1 or -10 and -1, right? In all cases I've ever seen scientific notation, they've used base 10. This does feel a bit odd to me as a computer scientist because I have a strong affinity for base 2, right? But I think like so many things are already structured around our notions being based on base 10 that it doesn't really make sense to use a base other than 10, right? A kilogram is fundamentally 3 orders of magnitude larger than a gram. There's no reason to change that. So here are some examples. There are some very big and very small numbers. The speed of light is 300 million meters per second. And we represent that as 3 times 10 to the 8th. And for me, it is much easier to tell that this is not 3 billion than it is to tell this is not 3 billion. Even including the commas, it helps a little bit, but that can be quite confusing. And also, by convention, we don't include commas with decimals. So the smallest mass unit I'm familiar with is the gram. And the mass of an electron in grams is quite small. I don't know how many zeros this is. In fact, the way I would figure out how many zeros this is, if I had to, is I would take that, I would copy paste it into Python, and I would calculate the length of the string. That would be the only way I would think I could reliably calculate that number of zeros, right? And so, to me, it is much more natural to express the mass of an electron as 9 point something times 10 to the -28th grams, right? So, very, very close, 10 to the -27th grams, right? that makes more sense to me. There's also some economic examples. Different people have different opinions on the inclusion of economics in the sciences or into scientific computing. It looked to me like a lot of the really high-performance computing stuff was being used by people in the financial industry, so I've preserved some of these examples. Let's just take a look at this. This is going to be the labor market outcomes of college graduates by major. It is maintained by the Federal Reserve Bank of New York. Can I zoom this in? So, let's take a look at an example. I always sort by median wage early career. And I do that because computer science is the highest when I do that. So that's always good. So let's take a look at these numbers here. 6.1%, that's 0.061. So I would represent that as 6.1 times 10 to the negative 2. And in fact, every percent is times 10 to the negative 2. Many of us in computer science are underemployed, right? So we don't have the jobs that we're hoping to get necessarily. So that is 16.5%. So that is 1.65 times 10 to the negative 1. Our expected median wage early career is 80,000. So that is 8 times 10 to the 4th. Is that right? Let's check. 8 times 10 to the 4th. And so it is. Then we have a higher, let's see, that one's computer engineering. Computer engineer salaries go up more later in their career. But fewer of us have to get graduate degrees. So you're in this 32.8% because you're working on your graduate degree, right? So that's 3.28 times 10 to the negative 1. So that's just some examples there. So I've expressed these as follows. Go ahead and close that. Wait, I thought I closed this. Okay. 11. Okay. Let's go ahead and use some arrays. Let's check the time as well. Oh, I have a text message. Okay, I'll do that now. And take another bite. Were you able to find any breakfast today?
No.
Okay. Sorry about that.
I had a sneakers while I was.
Yeah. Okay.
I don't understand. Courtyard, they don't have breakfast included. It's $130 per night.
Oh, that much?
Yeah.
Yeah. Oh, okay. I don't know. Stay at Wingate next time, as this was free. Do you want one of these? I can give you this one.
No.
Okay.
I don't eat much of a peanut butter.
Yeah. Okay. All right. Let's inspect the array in the same way we inspected the list of lists. And why are we doing that? Well, we want to know what's the same and what's different. We might have some intuition on how we work with lists. We might know about to-do lists from real life. But of course, in a to-do list in real life, you can add things to the end and cross things out in the middle. We can't really do that with an array. Arrays are fundamentally different in that way. So let's take a look. We have taxes, and we have our array. Let's look at the first house on the block of taxes. There we go, 9275, comma, 0.1. If we look at R0, the first house on the block, we see the same thing, but it's stylized quite differently. So first of all, it's clearly labeled as an array. That's nice. The values are in scientific notation. And actually, those are the only two differences, right? So nothing particularly too different about that. We can check the type of everything. So the type of R is a numpy ND array, and the type of R0 is also a numpy ND array. So it's an n-dimensional array of n-dimensional arrays, right? We're going to introduce slicing here, and I'm going to do this using colors. So I'm going to import I'm going to copy paste the color data into my Python. Okay, so here's colors. I just did them in rainbow order, which I think of as red, orange, yellow, green, blue, indigo, violet. The color scientists call this Roy G. Biv, and it's quite common because the first letters are Roy G. Biv. So I'm going to make a list of colors, which I'm going to call color list. And I'm going to make an array of colors that I'm going to call color R. So that's going to be an np dot array of colors. Okay. Then we can look at the color list, and we can look at the color R. One of the benefits of doing things in this way with colors is we're back to a one-dimensional array. Taxes were two-dimensional, so we'll get to do some things that are nice. Oftentimes we don't want to work over the entirety of our data set all at once. We might want to work over a subset of it, and one of the ways to specify that subset is with slices. For a slice, we take a starting address and a cutoff address, and we look at all of the addresses from this first address up until before this last address. So if we look at color list 1 to 4, what's that going to do? Well, color list 1 is the house at address 1, so that is orange. It is not red, right? Red is on the corner. Yep. Yeah, this is red. So we'll do 1, and then we'll go to 4. And we're gonna walk all the way to 4's house, but we're not gonna ring the doorbell. We're not gonna go inside. We're just gonna look at it from where we are. So we're gonna look at houses with addresses 1, 2, and 3.
So we won't take the last one, that fourth one.
Yep, we leave that out. And so color 4, color list 4, is blue, but we don't go to the blue house, right? We look at the red, orange house, the yellow house, and the green house, right? We can do the same thing with color array. 1, 2, 4. This array now, and I don't want to pretend I'm not looking at this here. This says dtype less than U6. What that means is there's fewer than 6 Unicode characters in it. Don't worry about that. We're not going to put strings in NumPy arrays that often, and when we do, we're not going to care about how they're stored, right? But this is making sure we know that these things are not integers, right? Which we do know that, okay? But hopefully we get the same colors here: orange, yellow, green. Perfect. I'll take another bite here. I thought I managed to fit this one on my screen, but I didn't. That's okay. So we kind of line this up here a little bit. We start at 1, and we stop before we get to 4. So we do orange, yellow, green, and we stop before we get to 4. I think a lot of times you're like, when there's a Pizza Hut at the corner turn, you turn before you get to the Pizza Hut, right? That's the same idea. Let's zoom back out. Okay. Slices are quite nice to work with, and they might be non-intuitive, but they are fast, right? So when you get used to them, they're nice, and that way they're sort of similar to Vim, right? So we can do a few things with them, which is we will refresh what color R is, which is Roy G Biv, and then we will take, starting at the 0th house, the house on the corner, which we already know is red. We will stop before we get to the 4th house, so we're going to stop at the green house before we get to the blue house. We can express this in the exact same way by leaving out the 0. So if you leave out the first value, it is interpreted as a 0. That just saves you some typing. I would have expected the 0 to be used as like a special thing, that if you put it in, it does something special. It's just not used at all, right? So these things are equal to each other. Oh, it checked to see if all of the elements were true. Let's try it with a color list. There we go. The lists are the same. Very good. We can also omit the last element, but this is a little bit more complicated because this is related to the length. So let's calculate the length of our color array. I'm going to store it in something I'm going to call, well, I don't want to call it L because L's look like 1s. So I'm going to call it S for size. So I'm going to say S is the length of the color array. And I can also say it is the length of the color list. Length is a built-in function just like type. So we have a few of these things around. We happen to have length, right? Given that we have the size, we can look at color array. And we can now start at the 4th house, which I believe is green in color. I could be wrong. And we can go to the end of the list, which we've determined is S. So it's the blue house, it's not the green house. So we see blue, indigo, and violet, BIV, in our Roy G BIV, right? And that is the same as if we just omit the S. So that is quite helpful for our purposes. And then we can once again verify that the lists are the same when we do this slicing. Okay? Have you used slices before much?
Yes.
Okay. Well then, hopefully you're familiar with the step size. I like to use steps mostly when I load in a relatively large data set, so at some point we're going to load in the periodic table of the elements, which has 118 elements in it. It is hard to print out all 118 elements, so what I did is I looked at every 20th element. That was very easy. There were 5, right, or 6. And so that was much more manageable, so I used a step size to do that. Let's show step size. We can look at color R, 1 through 4 again, right? And that is O, Y, G. We do not have the red value. We start at orange. And this is equivalent to looking at starting at the 1st house on the block and stopping before the 4th house on the block and looking at every house. But we might want to look at every other house. So this 2 says, rather than going to 1 house and looking at the next house, go 2 houses and look at that house. So if our color R is like so, we start at house address 1, and then we go 2 addresses to green. We can do orange to green to indigo. And we can do red to yellow to blue to violet. With the full length of the entire array, we can also do bigger jumps, so we can do red, skip 2, green, skip 2, violet. And if we skip more than that, then we start only getting 2 houses, right? Red, skip 3, blue. We can't skip 3 and get another one. Right? So this is the 3rd value, the step size, mostly useful in taking samples from large data sets, right? That's when I really see it. When else do we use this? So if we had taxes and we hadn't expressed that as a list of lists, if we'd just done price, tax rate, we would be able to pull out the taxes by using step size, right? Because this is odd numbered, this is odd numbered, this is odd numbered, this is even numbered, this is even numbered, this is even numbered. So if that was all one list, is there, let's see. I don't know if I can flatten this. I don't know. Some languages have something in them called flatten. Okay, so if this were just a list of values and not a list of lists, we would be able to use the step size. So here's a good example. We can look at 2, every other element, okay? So I don't know what you learned in kindergarten or what you remember from kindergarten. I remember at some point I found out that kindergarten was just German for children garden, and I don't know if that's the garden they put the children in or the garden that the children come out of, right? Like, do you plant the children and they grow? I remember like having regular drink and snack breaks in kindergarten, and I wonder if that's because they were watering me like a plant so I would grow. That's my theory. But anyways, in kindergarten, the Garden of Children, I learned that red, yellow, and blue were primary colors. This seems to not be true. It seems to be the case that red, green, and blue are primary colors, or cyan, magenta, and yellow are primary colors, so I don't really know what my kindergarten teacher was teaching, or maybe I was learning wrong. It so happens to be very convenient that I learned that the primary colors were red, yellow, and blue, though, because those are an example of steps. So we can express those as follows. If we have color R, we notice that red is a step size of 2 from yellow, which is a step size of 2 from blue. So if we look at color R, take the 2 step size, we have red, yellow, blue. We also have violet. That's no problem. We can cut off violet by saying we need to stop before the end of our array. And that gets red, yellow, and blue. And this also gets red, yellow, and blue. Because whether we stop before the 5th or the 6th house doesn't matter when we're going 2 houses at a time. And this is also the same as starting at 0 or not starting at 0. So those are the primary colors I learned in kindergarten. I think the theory was if you mix perhaps red and yellow, no, if you mix yellow and blue together, you get green. So green's not a primary color, is I think what I was told. Uh-oh, we might have a guest. Look like you're working hard. Okay. That's not how you spell emissions, right?
I think it's 1 M, I guess.
Yeah, it's one M. That's wrong. Okay. So, we can omit the start, stop, or both, and still take steps. And then, most usefully, pretty much only see this with -1, but you can take negative steps. So you can start somewhere and then look at the house before you. This makes perfect sense, right? If we're looking at a block of houses, right, you don't know which side of the block you're going to start at, and you can still look one house at a time. Let's take a look at this example. We can say color, ::, -1. Oh. Color R, -1. This gets a lot sillier if you start saying where you start from. Because that started from index 1 and then went negative, right? And we can also use negatives here, and they go from the end of the list. So this is, yes, address, because it's 1 from the end of the block. All right, so that's everything. This is what? The 4th one from the end of the block. 4, 3, 2, 1. And we notice we do say that is 1 from the end of the block. We don't say that's the house at the end of the block, right? So, there are our slices. I pretty much exclusively use this to reverse things. That's all I use it for. Reversing things is pretty useful. So taxes, sometimes I've been calculating these by starting at $0 and going up. Sometimes I've been calculating them by starting at however many dollars you have and subtracting down over time. So it is in fact the case that it is often useful to be able to do this, right? That does come in handy, right? And this one's pretty easy. You can imagine how you would calculate taxes here. You say, hey, you pay 39.6% until you get to this value. Then you pay 35% until you get to this value.
Close the door?
Well, last time we closed it, we had a hard time getting back in. Yeah, we close it. We just have to remember to not open. Yeah. But where's omission? Oh, it's capital O. There it is. There we go. There were other typos, right? Were there? Maybe there weren't. Everything else seem okay? Yeah. I don't know. Okay. All good, I guess. Okay, cool. So, we can use the negative stops and starts. So we can say color R, and we can go up till 2 from the end, or we can go up till 5 from the end, right? We can start some distance from the end and just see the last 2 things, right? We can see from the last 5 to the last 2 things, right? So yellow, green, blue, and that would have indigo and violet after it, and it would have red and orange before it. All right, so that's the middle of the list. I think that's pretty much the same as doing 2, 5. Oops. Yellow, green, blue. So in those cases, when you're getting to things in the middle of the list, it doesn't matter what the positives and negatives are. Okay. There is one pretty interesting difference here between Python lists and numerical Python arrays, and we're going to look at it here in the context of taxes. So we'll recall what taxes are. If we look at the taxes, okay, we're not going to look at the initial tax bracket. We're going to look at the, I don't know, the first non-base tax bracket. So we're going to go to 1, and then we're going to look at the rate for that tax bracket. So that's taxes 1, 1, and we're going to get 0.5. We recall R has the same information in it, so we can look at R 1, 1. And we can look at the 1 addressed element of the 1 addressed NumPy array, right? And that makes sense because we can look at this and then we can see that if we look at the address 1 of that, we get 1.5 back, right? Something that's a little interesting that you can only do with NumPy is you can do the comma notation and get the same values. That is really not allowed in Python. That just doesn't work. This can be pretty nice. Maybe it can be annoying. It's up to you. But it really matters more so when you're looking at slices. And so coordinate slices can be quite goofy. One of the things I realized I might want to do is I might want to reverse taxes, right? So I thought taxes looks like this, and I thought, well, can I reverse that? And then can I reverse the insides too? And you can't. That actually just reverses the array twice. Do you see how that works, right? We have 9275, 9275, 9275. So it's just changing the direction back and forward, and I can do it again. However, with a NumPy array, yes, I can reverse the array once, as expected. And so that's the reversal. It's 4 to 9 instead of 9 to 4, right? But because I have commas, I can also reverse the internal elements. And this is really nice. I can reverse and just look at the brackets. And there's no real way to do that with taxes. That's just going to give me one of these elements. So the parens become very useful as soon as I start using, or not the parens, the commas become very useful when I start using slices, and they don't really matter until then. I thought it was really cool I could do this. This is quite tedious to do in Python. I'm not even going to show you how to do it because it's so annoying. And of course you can, of course it's possible, right? But NumPy is about making things easier, and this was one of the first things I noticed was easier. The real difference between an n-dimensional array and a list. It might occur to you, and this might be interesting to you or not, if you can do this, oops, it also means you can do this. Nothing, comma, 0. Oops. Is that fine? Oh, I thought I could do that. There's some way to, right, you just put a hole in there. So there's ways to see all of the first or all of the second elements of a NumPy array. And there's no real graceful way to do this with taxes, right? So if I do, I don't even know what it would be, right? Like this. Yeah, it just doesn't work. Right. NumPy arrays are not unlike, excuse me, NumPy arrays are not unlike the lists in the way that we can update them with single equals assignment. We'll look at the example of color R. When I learned, the only time I was ever taught color science was literally in kindergarten. After that, they just assumed I didn't care what complementary colors were, which was too bad because I cared about it a lot. I don't really know what indigo and violet is. Indigo, at least, is the name of a plant, so I know what that is. Violet was a little bit ambiguous to me. And so I remember asking, I said, well, what's a violet? Because I thought violet was a flower, and I thought the flowers were white, too, which I don't think is true. But, and I said, oh, well, violet is just purple. And so that's why isn't it called purple? Well, now that I'm in NumPy, I can say that it is purple. Oops. It's not pupil. How do you spell purple?
P-U-R-P-L-E.
Is that okay, that looks good. Does that seem right? There we go. Purple. I knew whatever I want. Now that I have the power of Python, I can change what the colors in the rainbow are. I can change indigo to, I don't know what I'd change indigo to. Bluish. There you go. I think there's something I can't do. I don't know if I'm allowed to change this.
Indigo is same as purple.
Is it?
Yeah.
Oh, we should have changed indigo to purple.
Yeah, dark purple is blue. Purple is blue color.
It's great. So in between blue and purple, we have a purplish blue color. Okay. Thank you. How extremely helpful. Okay. Well, bluish is not bad. Here, we'll change it back to bluish. Yeah.
Doesn't matter actually.
Yeah, it's bluish. It does kind of feel like there's 4 colors, red, orange, yellow, green, and then blue 3 times. But whatever. So we've introduced some niceties in NumPy, but we haven't really shown how it actually speeds up scientific process, how it actually really takes advantage of what's going on in the computer. We've probably already correctly inferred that if you had access to a spreadsheet, it would be easy to select rows or columns, and it would be easy to reverse either of them, right? What else can we do? Vector operations. We can multiply NumPy arrays by values, and the values change. We can multiply 2 NumPy arrays times each other, and the values will change, right? This is unusual. Take a look at first 2 examples. I'm going to create a list L1, which contains 1, 2, 3. I'm going to create a list L2 that contains, I'm not going to do 1, 1, 1, I'm going to do 4, 5, 6. Okay? If I add L1 plus L2, I get 1, 2, 3, 4, 5, 6. If I add L2 plus L1, I get 4, 5, 6, 1, 2, 3. If I convert these to NumPy and I create an R array, A1, that gives me my NumPy array, and I'll make a corresponding A2. I'm going to get very different operations. If I add A1 to A2, I'm going to do vector addition. 1 plus 4 is 5, 2 plus 5 is 7, 3 plus 6 is 9. And also, this helpfully preserves something that I like a lot, which is that I often think that when I add 2 things together, the order in which I add them shouldn't matter. But with Python lists, it does matter. L1 plus L2 and L2 plus L1 are different. Those aren't the same thing, right? But A1 plus A2 and A2 plus A1 are the same thing. Because this addition is vectorized, that means double equals is also vectorized. So if I compare A1 plus A2 to A2 plus A1, I'm going to get 3 trues, because it's saying the 5 is the same, the 7 is the same, and the 9 is the same. I can also demonstrate that by comparing A1 equals A2, where none of them are the same. And to demonstrate that in fact some of them are the same, I'm going to take A2, I'm going to update its 0th value to be 1. Is that right? Yes. And then I'm going to do the comparison again. Well, I'm going to look at A1 and A2 to make sure I did that correctly. So the first value in each is 1. And so we see when the values are equal, we get true. When they differ, we get false. When they differ, they get false. This is our first high-performance computing idea, is vectorization. I thought vectorization was a big deal and was going to stay a big deal for a while. There is another high-performance computing language named Julia that seems to not use vectors. You just write loops and it figures out there's vectors in them. I don't know. The data science people seem to really like vectors. None of them know how to write loops, so they like vectors a lot. So I don't know if vectors are here to stay or not. They were here to stay for a while. I am a computer scientist. I study hardware. There are vector operations implemented in hardware. GPU operations are very close to being vector operations, and CPUs also have vectorized operations that work over smaller integers, right? So I think writing code that has these vector operations in it is probably a good way to go. I was in Portland when I was designing these slides, so I took the high and low temperatures from 526 to 62, and I took it in degrees Fahrenheit because I was in the United States. And I do apologize for being in the United States. I couldn't do anything about it. So we'll call these the Portland temperatures. Okay. Now, let's take a look at this example. Now I could say pdx minus equal 32. And that doesn't work, because pdx is obnoxiously still a Python list, and nothing works with Python lists. So I'm going to convert that into a NumPy array. I'm going to call it temps, and it's going to equal np.array of pdx. Okay. Now I'm going to look at temps, and now I can take temps, and I can subtract 32 from temps, and we'll see that all of these values are 32 less than they were before. After I subtract 32 from temps, I can multiply it by 5. And so that's temps minus 32 times 5. Now, you might not see where I'm going with this just now, because multiplying things by 5 is perhaps a bit odd, right? But my understanding is that a Celsius degree is 5/9 of the size of a Fahrenheit degree. And that's not too bad to remember, because, stick with me here, Celsius is 100 degrees from 0, which is freezing, to 100, which is boiling. In Fahrenheit, freezing is 32 degrees, and boiling is 212 degrees. 212 minus 32 is exactly 180. 180 divided by 100 is exactly 5/9, or 9/5, right? Right? And we can see that by taking 212 minus 32, divided by 100, get 1.8, which is the same as 9 divided by 5. Okay. So I have temps minus 32 times 5, and then I'm going to divide by 9. Okay. And that gives me all of the various temperatures. let's step through this example over here, and we'll do one additional thing to point that out. Notice the real difference here is that I used a single slash division, and these values are decimals, and these values are not. We're going to find one of the things that a NumPy array does for us. So we have temps. We can take temps and we can subtract 32, like we did here. I'm going to use minus equal to update it in place, right? So that actually changes what temps is. I can take temps and I can take it times equals 5. That is going to update temps. And then I can take the temperatures and I can divide equal 9. But I can't do that. And why can't I do that? Well, what is temps 0? Temps 0 is 190. And what is the type of temps 0? Temps 0 is an integer. It is a NumPy int 64. I'm on a 64-bit computer just like the Nintendo 64. Me and the Nintendo 64 were just like this, where we go way back, right? And so, what is the type of temps divided by 9? Not an integer 64, which means I can't put that value into my integer 64 array. So I have to use the special integer division, which is 2 slashes, which gives me back an integer, which gives me back an integer, which gives me back an integer. And that's sort of one of the properties of NumPy arrays and floating point numbers and so on. I didn't realize how much more I would like this, right? This looks pretty nice to me, but there are some things we should point out. This here is a 13.8889. We would probably perceive that as 14 degrees Celsius, but I got it as 13 degrees here, right? So these are all truncating. They're all rounding down. So these temperatures are actually on average lower than these temperatures. I don't know if 70 degrees feels like 21 degrees to you, but what did the 13 correspond to? 57, right? That is decently different, right? I do think of 57 as 14 degrees, I guess. I don't know. I don't look at the temperature before I go outside in the morning, so I like come back inside and say what temperature was it and then find out. So I don't have a strong sense of temperature. So let's take an aside on integer division. NumPy requires arrays to be a certain kind of number, and actually a certain kind of thing. They can be strings as well, right? 30 is an integer. 30 divided by 9 is a decimal value. 30 double divided by 9 is an integer value, right? And so we can see this example right here. We get a bunch of integers back, or we get a bunch of fractions back, right? If we create some array, which I'm going to call sum because I already used array, the sum array is only containing integers, so this is allowed and this isn't. So I get to divide by 3. But I can keep dividing this by integer dividing by 3 as many times as I want, right? There, and now they're all divided to 0, right? So, because in NumPy sometimes you are forced to stay with integers or floats, you do have to know about integer division. Integer division also comes in handy if you're trying to compute ranges or indices or something, right? Because those also have to be integers. I can look up the 10 divided by 3 is not a valid index for an array, but 10 integer divided by 3 is a valid index for an array. And there it is. 10 divided by 3 is the third address. So we have 0, 1, 2, and 3. Okay. Now, I think slices and vectorization are probably the correct way to do the income tax example. That was one of the reasons I selected it as my contrived example. So we'll go ahead and take a look at that. Fine, check. Okay. So when I look at taxes here, I note I don't have the 39.6% tax rate anywhere. Okay. That's one annoying thing. I feel like what I really want with this, which is the 10% tax rate, I want that to correspond from 0 to 9275. And I don't really have the 0 specified anywhere. You remember when I wrote the loop over taxes? I had to save the end of the previous bracket and use it as the beginning of the next bracket. And that was kind of goofy. I thought that led to an unreasonably difficult to understand for loop. So we're going to solve all of this by using vectors. How am I going to do this? Okay, so I have my array. Got my array over here. It's the same as the array over there. We have 0 to 9275, 9275 to 3765. So we need 9275 in 2 tax brackets. How are we going to do that? No problem. First thing I'm going to do is I'm going to extract all the cutoffs. So how am I going to do that? Well, I want these values. These are each one of these has some address on the block, but it is always the closest house to the street. So I'm going to say cutoffs equal array. I'm going to say I want all of the lots on the block, but I only want the first floor apartment, the ground floor apartment perhaps, right? So that's cutoffs. 9275, 37650, and so on. And just so we know what it looks like, we could get all of the rates as well. That's no trouble at all. When we look at it this way, I think it's also much more clear that we're definitely missing a rate. We know there's a pre-396 tax rate somewhere, and it's not written down. So what are we going to do? Well, the initial tax rate, or the initial tax bracket begins at 0. It doesn't begin at 9275, and the final one ends at infinity. I'm now in NumPy, so I actually know about infinity. There it is. It's infinity. Don't try and divide it by 0. It's against the rules. In fact, anything you divide it by, you're going to get infinity back. Divided by 10. Divided by Google, and it's still infinity, right? Pretty much anything we multiply it by, we're going to get the same value as well. But I think we can make it negative, right? Then we can get it positive again. So we do have infinity, and we're able to take our cutoffs and use infinity with them. I'm now going to introduce NumPy insert. I'm going to use NumPy insert to add a value at the end of an array. So NumPy insert takes 3 arguments, A, B, and C. Argument A is an array, argument B is some index, and argument C is some value. Let's take a look at a few examples. So we can np.insert into cutoffs at index perhaps -1, np.infinity. And that didn't work very well because that put it before the end of the list, right? And I don't think I can specify -0 either, because that's the same as 0. So what I actually have to do is I have to figure out the length of cutoffs. And then it puts it right at the end, right? I don't know what happens if I do length of cutoffs +1, but I'm guessing it just goes to the end. It just exceeds my bounds, right? This also means I can put things at the beginning. This will be not the house on the corner, but the next house, right? And I can also put in the house on the corner, right? So I can put infinities in here wherever I want. And notice infinity, it looks like text, but it's just being treated the same way as any of the other numbers, right? So what I really want is I want cutoffs equal np.insert into cutoffs. So I'm going to create a new array, and I'm going to save it as cutoffs again. I can't change the size of my arrays, but I can make new arrays, right? We're going to put it at length of cutoffs, and we're going to put np.inf there. And that looks okay to me. There we go. We have an infinity cutoff at the end. And so that's one way to add elements to NumPy arrays. Okay? I am unaccustomed to using insert, and the real reason I am unaccustomed to using insert is the example I showed you right here. I find it difficult to insert things at the end of lists, and I'm often trying to insert things at the end of lists. So instead I use append. Append does not take a value. I can show that. np.append 0 cutoffs. Oh wow, it does? I didn't know that. Okay, I thought that didn't work. We can also append, oops. We can also append an array there as well. That's good to know. Okay, hold on. Oh, the brackets aren't working. Let's see. np.append. Including scalars. Okay. So here is how we can add A0 to the beginning of our list. I'm going to call this cutoffs now, and I'm going to use the scalar. Okay, so what does cutoffs look like? Well, now we have all the brackets. We have 0 to 9275, 9275 to 37, 37 to 91, 91 to 19, 19 to 41, 41 to 415, and then 415 to infinity, right? So those are all of the tax break cutoffs. If you earn infinite money, you still only have to pay 39.6% of it to the government, which is very odd because if I take np.infinity and I subtract 0.396 times np.infinity, oops, that means that your amount of money doesn't exist, because you pay an infinite amount of tax. Oops. Oh my gosh, typing is really getting me this morning. What am I trying to do? Okay, there we go. So if you pay 39.6% income tax on your infinite money, you pay an infinite amount of taxes, but you still have an infinite amount of money left over. So you just get two infinities. And that's why we should tax people with infinite money at a very high rate, because we get a larger infinity, yeah. A lot of people have a hard time finding government programs, but I found this in NumPy, so I'm not sure what the difficulty is, right? and you get this every year, by the way, right? So someone with an infinite, yeah, as someone with an infinite amount of money, they can never spend all of it. So they have an infinite amount of money every year, but you can tax them infinity every year, right? So you actually have a larger infinity than they do, because you have an infinite number of infinities and they only have one. Isn't that cool? That's why the government's so powerful. That's why people have governments. It was actually an infinite money hack. Okay. So we can look at our cutoffs, and we can look at the beginning and end of every text bracket. And I'm just gonna type this out as I did. Well, we'll review what cutoffs is. The beginning is cutoffs. Infinity is not the beginning of any tax bracket. So we're going to say cutoffs, and we're going to go right up to the end. Is that going to work? Yes, we're going to. Oh, nope. We got it. What did I do wrong? That looks like it should be wrong to me, but... Right, isn't this what I want? Oh! I looked at cutoffs instead of begin. Okay, hold on, okay. So here's begin. These are the beginning tax rates. 0, 90, blah, 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 right? And then we also have the ends, which are the cutoffs that begin at 1, okay? There we go. So every tax rate is from begin to end. Can I put them next to each other? Not gracefully. But I can put them in an array either. So we'll say brackets equals np.array. Now I would expect that I could just put begin, comma, end, but that doesn't work. I have to construct it from a list of arrays, which is fine. And there we have it. Right. 0 to 92, 92 to 37, right? And so these all line up, and these are all now my tax brackets, right? We can also see how big each bracket is. See how many dollars in a row you can make without going up in your tax bracket. And we do that by taking end and subtracting the beginning. So we sort of knew how big the first tax bracket was. But this one really surprised me. There's a tax bracket where you only pay the 35% rate on $1,700. That seems like a lot of work for probably we didn't need to have that tax bracket, right? You know, it seems completely reasonable to start the 39.6 bracket at either of these two values, right? Especially given how big this one is, right? This tax bracket is as big as all of the previous tax brackets combined. And it's only at the 33% rate. It is unreasonable for me to think that someone that makes more than twice as much money as someone else should be being paid, or should be being taxed at exactly the same rate, but in fact they are. So that's our bracket size. The bracket size might be very interesting to you because, of course, this was used to calculate intercepts, right? So you can take a look at that. We do have to be very careful, by the way, though, that we do have an infinite size tax bracket. No matter how much money you make, you never have to pay 40% income tax. I think there's some nervousness about the top tax rate going over 50% because that might mean that your people with infinite money actually lose money over time because you're taking more than half of their infinity every time. So we're going to do vector multiplication here. We're going to see how much tax is spent within each bracket. And I'm going to get rid of the last bracket because it's of infinite size and it doesn't really make sense to study, right? So I'm going to take my brackets and, excuse me. I'm going to take the last one off the end. There's my brackets, okay? I'm going to multiply these brackets by the rates. I don't think I currently have rates. Let's see. Taxes. Let's get, R. So the rates are equal to R1. The first floor apartment. Every single apartment building I drive by. So those are the tax rates. All right, so I can take the brackets times the rates. Ooh, they're not the same size. Brackets. Bracket. Wait, brackets? Oh no, it needs to be begin minus end, right? Okay. Did I make that up? I need this, I calculated it somewhere. Right, yes, it's end minus begin. Ooh, first try. Okay, nope, not first try, okay. End minus begin. And that still has the infinity in it. Okay, all right. We're doing our best here. We'll take end minus begin, and that will be bracket size. And then we'll take bracket size, cut off the last one because it's infinity. Then we'll multiply that by rates. There we go. Okay, so what's going on here? Let's look at the tax rates again so we can see. Say we're making $500,000 a year, right? We spend about $1,000 in the first tax bracket, $4,000 in the second tax bracket, $13,000 in the third tax bracket, $27,000 in the fourth tax bracket, $74,000 in the next one, and then we only spend $600 in that very small tax bracket at the end, right? So most of our tax we actually pay in this sort of intermediate bracket here at the, what is that? I guess at the 33% rate? Yeah. So even if you make $500,000 a year, you're mostly paying taxes at 33%. Right? And then if you add all of these things up, that also tells you how many taxes you pay at the start of that bracket. So how do we do that? Oh, I'm going to call this thing bracket cost. Yeah, let's save this as bracket cost. Okay. Bracket cost equals bracket size -1 times rates. There it is again. Okay. So there we have that. Now, something we might want to figure out, and this is sort of what we were trying to figure out previously, is say I make $100,000 a year. Well, just like how many taxes should I pay, right? And we can actually figure that out now because these are the points in our slope point form, which is not yet slope intercept form. But what we really want to know, right, is if someone makes $100,000 a year, what do they pay in all of the previous tax brackets? And why do we want to know that? Because we're going to add up the cost in all of the previous tax brackets, and then we're going to tax them at, 25 or 28% on every remaining dollar. So there's actually a built-in function that does exactly this in NumPy because it's so commonly done. And essentially, if you do calculus, we're essentially taking an integral here. We're going to take a cumulative sum. So we're going to add up all of the previous rows in our table, or entries in our array, or houses on our block, whatever you want to say, and we're going to see what it looks like. And so we can take total cost, which is the cost not incurred in a single tax bracket, but the cost incurred in all previous tax brackets. And what does this do? Well, total cost. So, yeah, it's easier to see over here. And bracket cost. This value from the cumulative sum is equal to this value plus this value. It is about 900 more than that much. This value is equal to the sum of these two values. So all previous brackets and the current bracket. So it's about equal to 5,000 plus 13,000. So it's about 18,000, right? This value, 46,000, is about equal to its previous value, which is around 19,000, plus this value, which is about 28,000. So 28 plus 19 is around 47. So I rounded too much there, right? And so on. So someone making over however much money this is has paid this much money taxed at lower rates, ranging from 10 to 35%. Right? And we'll notice, again, these two values are quite close together. The big jump is right here. And this is the same thing we tried to calculate last time, right? Using single tax. So, what are kind of the takeaways here? Let me check time. Okay, we're doing well. NumPy does a lot. It does a lot of very cool things. Mostly it works with arrays. It does these vector operations. I'm going to stop calling them vector operations going forward now, and I'm going to start calling them broadcasting. Broadcasting is the term NumPy uses for vector operations. The reason for that is NumPy isn't really working with vectors. A vector is a specific mathematical operation that's not quite the same as an array. And so some of the things that happen to arrays are not quite the same as what happens to vectors. So I try to refer to vectorization without saying vector operations, but usually this is called broadcasting. And it's called broadcasting because if you multiply an array by one value, it's sort of like all of the houses on that block get to watch the same thing on their television, and it changes them all, right? So we send the same number to every element of the array, it multiplies, and then we get the array back. Indices and slices matter a lot. These are all links to NumPy documentation, by the way. It can be really helpful to have a constant like infinity, right? It made a lot of our operations easier. We were able to just sort of multiply things that we wouldn't have been able to multiply otherwise, and then we can just cut it off at the end when we didn't want it anymore. And then NumPy has a series of built-in functions that allow us to take advantage of all of the nice things an array can do. And I think I haven't shown you all of them yet, but for example, you can just directly compute a mean in NumPy, right, if you need to do that. It's built in. I don't compute a lot of means, but if you do, you can do that. I'm just going to read this out loud to you because I think it's important that you've heard this. You might hear of a zero-dimensional array referred to as a scalar, so an integer is a scalar. A one-dimensional array as a vector, a two-dimensional array as a matrix, or an n-dimensional array for size greater than matrices as a tensor. I have a strong preference for using the appropriate mathematical terms to refer to these values. But in fact, a two-dimensional array is not a matrix. A two-dimensional array can represent the same values in a matrix, but what makes something a matrix is the way matrix multiplication is performed on the array, and it is not necessarily the case that all of the matrix operations are the same on a two-dimensional array as they are on a matrix. So, for clarity, it is best to avoid the mathematical terms when referring to an array, because the mathematical objects with these arrays behave differently. They are the same while at rest. They contain the same numerical values. But when we start adding and multiplying them together, they might do different things, right? So matrix multiplication is fundamentally different from array multiplication. And I think we can demonstrate that. mp.array 1, 2, 3, 4. M1, M2 equals np.array. I could be mistaken, but I think the identity matrix is 1, 0, 0, 1. And I think that is fundamentally different from matrix multiplication. I don't know how to do matrix multiplication in NumPy, but I don't believe that's how matrix multiplication works. I don't even really know what exactly this is all doing. So just be careful if you're multiplying 2D arrays times each other. They're probably doing pretty odd things. Let's see. How do I multiply matrix? Oh, it's matmul. Okay. Right. So matrix multiplication is very different than array multiplication. It is. I don't know what to say other than that. Oh, I think I see what this is doing. This is just doing multiplying the same values in the same positions, right? Because that's 1 times 1, that's 2 times 0, that's 3 times 0, and that's 4 times 1. So that's why we have the 1 and 4. It just zeroed out the 2 and the 3. But in this case, it did whatever matrix multiplication is. So, now it is time for your exercise, which is good because I haven't finished my breakfast and we probably need to go to the bathroom and get some water and stuff. So, I was going to get coffee. Ah, I forgot to get coffee. You have a Red Bull. You're way ahead of me. Okay, so here's our exercise. Today, we successfully recomputed the points of the point-intercept form of the income tax problem. Using NumPy and only vector operations, start with taxes, which I provide for you here. This is cut off a little bit. There was no way to not cut this off. These things just don't fit. They're just big. Starting with taxes, create the array on the right. What is the array on the right? It's the brackets, it's the rates, but it is also the intercepts. You've computed these intercepts previously using loops, because that was your assignment at the end of the day yesterday and last night. Now do so in NumPy. it is not too bad. You are going to probably be a lot happier if you use a transpose. What is a transpose? I have an example here, but I helpfully just typed in M1. M1.transpose changes the 2 and the 3. So it changes from rows to columns and columns to rows. Why might you want to do that? Well, the tax array could be dramatically easier to work with if you transpose it. So you might want to do that. You can also reshape things. So here's cutoffs. And that is currently a one-dimensional array. I think you can like reshape that into a two-dimensional array. How long is that thing? 7? And what this did is now it'll have different operations with respect to multiplication and division, right? So I can change it from a row into a column with reshape. So you can play around with reshape. I only used transpose, but I want you to be aware of them. The way that it made sense for me to do this, I really needed to use a transpose. And there's also a bonus problem, and you can see if your Python implementation is as fast as your NumPy implementation, which it shouldn't be if your NumPy implementation is good, but you can generate random values, time how long things happen, and so on. So I have a variety of solutions here and a variety of problems, so go ahead and work on this. And I'm going to refill my water and make some coffee and stuff, and you should feel free to get up and move around if you'd like to for a while. Okay. if I remember how I did this. I put my answers on the slides in case I didn't remember how to do something, right? Oh yeah, I see. Yeah. Okay.
Is there any way to turn the temperature a little bit down?
Oh, I have no idea. You can mess with this if you want, but I don't know what it does. So,
If you don't mind.
yeah, whatever works for you. I don't know. I think I was able to correct all of the minor typos in the slides and stuff, so hopefully you can see that in a couple minutes. I didn't correct as I was going last year, and last semester, all the automata things.
Yeah.
I'm like still finding just like minor errors in all of those slides. It's so confusing. Did you look back at them much at all?
Not much.
Okay. At least it's not bothering you then. It bothers me because that's the reference I use to understand automata theory too. Like I like Sipser's lectures and they're very good, right?
I want to see lectures. Yeah.
Yeah, so I definitely learned it from Sipser, but like I don't use that for reference material. I use my own notes. And I find his PowerPoint slides not great. His talking is very good. I hope I get to teach that class again. I would like to. I don't know what I learned from teaching it the first time, but I'm sure I learned something. How you doing on the vector ops?
And the code by nothing. I already installed the NumPy, but my VS Code still gives me error for the NumPy. I'm just trying to solve this one.
Oh, okay. Working on VS
It
Code.
works on the terminal.
Yeah, working in the terminal and not in VS Code is a good thing. That's teaching you what you're supposed to learn, which is to not use VS Code. I was chatting with some of the...
Let me try PyCharm.
Yeah. The other ones I'm supposed to tell you to try are Spider.
Spider?
Yeah, some of the scientists use Spider. For this class. So PyCharm is used for development, right? Spider is used by the scientists. And there's a group out by us called Posit, and they made something called Positron, which I haven't used. I don't know if it's any good. But they're very proud of themselves. And this looks a lot like VS Code to me. But that's very much it. Positron says, or Posit says data science. Spider says science. But this thing's pretty cool. You can see what it looks like here.
PyCharm gives the same error.
Okay. What's the error?
No module named NumPy.
Okay. You have two versions of Python on your system, and your IDEs know one and the command line knows the other one. And I wonder, do you type Python or Python 3 at the command line?
Tried both.
Do they both work at the command line?
I think Python worked at the command line.
Did Python 3 not work?
No.
Exactly. Okay, so what does that mean? That means, I don't know. So I have Python, right, which is 3.12. I have Python 3, which is also 3.12. My Python and Python 3 refer to the same version. Do yours. Check. Oh, you can just do Python double dash version to get it.
Check the Python version.
Mm-hmm.
No.
So they're different versions. That's because you have two different Pythons. Now, probably only one of those Pythons has NumPy on it. Now, see this command? The reason I recommend using Python 3-m pip is because that installs that installs the modules to whatever version. So, one of your two Pythons doesn't have NumPy on it. So, do both. So Python 3 m pip install numpy, and then python m pip install numpy. Now, for me, it's not going to do anything, right? But there's an even.
Okay, it's installed in Python.
Okay.
3.
Cool. I'll use the term bundling. It's likely when you installed either PyCharm or Visual Studio Code, it bundled a version of Python, and then that version of Python wasn't necessarily accessible at the command line. So maybe you have two, but you have two versions of Python on your system for some reason, right? Which means that anytime you install a package, you will want to be keeping track of which one you installed. On my Windows device, the one that doesn't have the 3 at the end is the one I manage. And the reason for that is that's the one I installed directly from python.org. And there is one called Python 3 that's managed by Windows, which doesn't get the latest updates. So I don't use that one. On this device, Python and Python 3 are aliased to each other. So it's referring to the same one. But in both cases, actually, unfortunately, they're both managed by Ubuntu, my operating system, because I would like to be using 3.14 with NumPy 2.0. I don't know what my pandas version is. There was a bunch of big versions of these that came out recently. Okay, I have pandas version 2. That's the important one to have a later version of. But okay. I guess we'll get started on this and then go get lunch. We'll probably just install matplotlib and then go from there. Okay, so feel good about the vector ops?
Yes.
I think that's a good way to think about the world, regardless of what you end up doing, right? You really want to be in the meeting at the company you work for someday and say, can't we vectorize this? And then everyone will think you're a genius, right? So, all right, what is matplotlib? Matplotlib is the plotting library. There are a lot of people, especially at the other university I teach at, that thinks there are plotting libraries other than matplotlib. Those people are basically wrong. And I'm going to show you the manner in which they're wrong, and I'm going to use a plot to do it. This is Google Trends. I oftentimes use Google Trends because I have to decide what to teach you. And so I look up some things. An example of something I look up is I compare the popularity of NumPy, and perhaps I compare it to MATLAB. And I don't just look at it in the past day. Usually I look at it in the past 5 years. So, MATLAB, enduringly popular, right? Let's make this a little more fair. And, actually no one is using MATLAB, right? People are just referring to NumPy as Python, right? They're saying, I do it in Python instead of MATLAB. This is pretty easy to tell. You can look at job ads and they say Python or MATLAB. They don't say NumPy or MATLAB, right? We can do this with some other things. We can say matplotlib, and we can compare the popularity of that to MATLAB. And of course, MATLAB's a little more popular, but we're seeing matplotlib is already about as popular as NumPy. And that's because the same people use them, right? To my knowledge, The other data visualization libraries are mostly in Python, and then there's one in JavaScript and one in R. So there's d3.js, which essentially doesn't exist. That's the JavaScript library. And then there's ggplot. This is the one used in R. Statisticians like it a lot. You will see ggplot is sort of on the same trend lines as matplotlib. It's becoming popular in data science, and visualization is popular and less popular otherwise. So it has the same dips, right? So that is the most popular non-Python library that I'm aware of. ggplot is the same thing as plot9 in Python. It's implemented. Absolutely no one uses plot9. The new hotness is Seaborn. Seaborn is built on top of matplotlib and it looks great, and you will see Seaborn is actually relatively popular. I thought about teaching you Seaborn. You would be welcome to learn Seaborn on your own. In fact, I'd encourage you to play around with it if you're ever making a graph. I basically don't make graphs in matplotlib. I make the graph I want in matplotlib, and then I import Seaborn and I make it look nice, and then that's the one I send to my boss, right? So Seaborn looks really nice. Check it out, probably on your own time, but I don't know, maybe that seems pretty to you. Looks good to me, right? There's two other pretty big ones, Plotly, and I do have an example of Plotly in the slides, and let's go ahead and get plot9 and ggplots out of here because this is getting hard to see. So we're just going to do the Python libraries. So these are Python libraries. Plotly and Seaborn, very close. Why do I not recommend Plotly that highly? Plotly's licensing is a bit sketchy. It's owned by this data visualization company that sells dashboards to companies. Myself and some other people that have been in computer science for a while are always nervous about teaching students something that might stop being free. We're worried you're someday going to need to make a portfolio project while you're between jobs, or you're going to be doing some contract work, and you're going to go to use Plotly, and all of a sudden it costs $1,000 a month to use. Plotly is my favorite one to use. I think it has really nice stuff in it. I don't think it looks as good as Seaborn, but it has better 3D, and the 3D stuff is very cool in Plotly. So Plotly is also really good wow factor, a little bit sketchy to use. Let me show you an example of Plotly. This is just a very, very impressive piece of software. Here's an example app. AI-based gene expression profiling. It's slow. Look at this. Look at that. Look how cool that looks. That looks great. You can make that. These things aren't that hard to make, right? This has mouse over on it, and I think I can click and drag. So Plotly does some cool stuff. And I have an embedded Plotly example in these slides, okay? And then the last one is Altair. Is that right? I gotta make sure. Altair plot Python. I might not be spelling it correctly. Yeah, it looks like Altair. This one is really popular with, I'm going to teach you Pandas, the competitor for Pandas that's about half as popular but growing in popularity is called Polars. Panda uses Matplotlib, Polars uses Altair. And you'll see Altair is, it had some spikes in popularity at various points in the past. But I started teaching data visualization around here in this era between 2020 and 2022. And there was a real thought that Matplotlib was going to go away. It looked like it was in decline. It looked like both Seaborn and Altair had times they were more popular, right? That did not happen, right? We hit 2022, everyone's back in the office, no one's sitting at home making plots for fun anymore, and everyone instantly goes back to using Matplotlib because it's the easiest to use, and they don't care that it looks a little bit worse. So I put a great deal of thought into this. I thought it makes sense to teach Matplotlib. Now, okay, there's one other thing you should look at on here. These are definitely trending upwards, these bottom three, and this top line is definitely trending downwards. That's certainly happening, right? So if you want to punch out and go to Seaborn anytime, or Altair. Altair is currently the winner, right? It wasn't, it is now. You should feel confident doing that. The real thing to know is I don't have to make graphics very often, at least in my career. I pretty much make 1 or 2 data visualizations a year to put in the results section of a paper. and I just decide what library I'm going to use. And it's not like I'm up to date and like great at matplotlib, so it's not going to be a lot of extra effort for me to use whatever other library is popular at the time, right? So in a few weeks, I'm going to be putting a graph in a paper, and I have to decide if I use Altair, Seaborn, or matplotlib. That's the only time I make this decision, right? And you might be making quarterly reports to a company vice president or something like that. So you're not going to be making graphs all the time, probably, unless you get a dashboards job, in which case you're definitely using one of these two, probably Plotly, right? Most of the time, someone's just going to say, hey, can you make a graphic of this real quick? And you're going to decide which one of these three things you pip install. That's it. And so my recommendation is use matplotlib unless you're trying to seem like you know what the new hotness is, and then use Altair. But make sure you don't use Altair to impress other people without being able to describe why you used Altair instead of Seaborn or Plotly. I think Seaborn's the easiest one to justify. I've always been able to go into meetings and been like, yeah, I switched to Seaborn because, I tried to do this thing in matplotlib and I couldn't get it to look good. And it looked great in Seaborn, and all the information was there. That was an easy thing for me to say. So I recommend talking about it that way. Let's put ggplots back on here. Yeah, it's below Altair now, so yeah, that doesn't really matter. Those are all in Python, and really, to my knowledge, the most popular non-Python ones are D3JS, which is from the Plotly people. It's the same thing, and ggplot. Okay, so what is matplotlib? It's the one. Scientific publications, the graphs in them are either made in Excel or matplotlib. I don't know why people still use Excel. People really good with Excel seem to really like it. And it just seems so sluggish to me, right? It feels like it takes a long time to turn on, and I'm like dragging my mouse across the screen, and I have a strong distaste for it, so I like matplotlib. All right. To the best of my knowledge, matplotlib gives you by far the most fine-grained control. There's an example in these slides where I wanted to label 1 point, and I did so, and it took like 1.5 lines of code or something. I could have done it in 1 or 2, right? Everything that you can do in matplotlib, you can do in Seaborn. Seaborn sits on top of matplotlib, so you can make a graph in Seaborn, and if there's something that's not in Seaborn, you can use the matplotlib stuff to do it. That was a huge justification for me definitely teaching matplotlib, because Seaborn's one of the modern ones, and if I teach you matplotlib, you also know Seaborn, kind of. ggplot, to me, is non-competitive because it's in R, and I find R a nightmare to use. It's not used by developers in a way that's very obvious when you go to use it. You don't realize how many things about Python, even when you're just using it for scientific computing, were fixed by software engineers, right? It's fast, the packages all work, it's just much nicer to work with. So I have a really hard time working with ggplots because I find the R ecosystem so frustrating. Altair and Plotly are mostly used for people that are doing business intelligence. Maybe you're going to do business intelligence someday. I don't know. I speculated you're not, so I'm teaching you matplotlib instead. It is entirely free and open source. It is the most free, and it is the most open source of all of these. The other one I use, and I use it all the time, is I use Plotly every time I want a three-dimensional plot. Matplotlib publishes to images, and Plotly publishes to web pages. And sometimes I want to open my graphic in a web page and click around on it and mouse over points and stuff. And Matplotlib doesn't really do that. It's fundamentally different technology. And Seaborn doesn't really do it either. So I begrudgingly use Plotly a lot. I haven't used Altair yet, but I'm going to start. And so if I see you in a year, I'll have more of an opinion on Altair. I sort of just found out about it, actually, while I was making these slides. What do you think I was trying to type there? Colon space hide. Okay.
Visualize.
Yeah, it's definitely visualized. But what was hide for? Yeah. And is it hide or is it something else? Was it like devisualize? Okay. All right, we got to get back to work over here. Let's see. nvim 5. Okay. So install. We just talked about how to install this stuff, right? So you know what to do. If you want to use it in PyCharm or the command line, you're going to have to do different things, and you're aware of that now, right? You have multiple Python versions of your system. Yep. Most people have multiple versions of Python on your system. I teach intro Python. Every student has a bunch of versions of Python on their system, and none of them are the correct version. I don't know why students love having multiple versions of Python on their system, but you do because you had multiple versions, so you know what happened to you. Let's go ahead and just make a sample plot real quick, and then we'll break for lunch. I'm going to exit and re-enter Python. Typing Python 3. I'm typing import numpy as np. I'm typing import matplotlib. .pyplot. What is .pyplot? So matplotlib was a MATLAB library. It worked exactly the way MATLAB did. All of the functions were named the same. Over time, the community added this pyplot interface to it. So it's the same matplotlib, but some of the functions have different names. For whatever reason, I learned the pyplot interface, which does not actually make my life any easier. So I'm teaching you the pyplot interface, which is often recommended. So I'm going to type matplotlib.pyplot, and I'm going to get the Python plotting interface. And I'm going to import that as PLT because I don't want to be making this many typos. I consistently for years referred to matplotlib as matlibplot, and you don't ever want to type that because your code doesn't work, right? It's just like it's like 3 nonsense syllables in a row, right? It's very difficult to work with. Okay, so downloaded and installed that. Let's plot something. Let's see, a period is a horizontal row of the periodic table. There are 7 periods in the periodic table, with each one beginning at the far left. A new period begins when the new principal energy level begins filling with electrons. You see that? I missed a space. Okay. So, this is the periodic table of the elements.
You're not pushing on Git?
Not between every minor edit.
Oh.
I push at the end of the slides. I have to, the markdown has to be rebuilt to HTML, so it's actually a considerable computational cost to build the website. But yes, they will be pushed. So, here's the periodic table of the elements. What's this represent? This is a hydrogen atom. It has 1 proton and 1 electron. This is a helium atom. It has 2 protons and 2 electrons. Those protons and those electrons are on the innermost electron shell, which is denoted by the rho. Now, lithium here has 3 electrons, but 2 of them are on the inner shell and 1 of them is on the outer shell. So what this means is that lithium only has 1 electron that can bind with other atoms. Beryllium has 2. Boron has 3, 4, 5, 6, 7, 8. So we have 2 outermost electrons, and then we have 8 outermost electrons. We can simply do a subtraction here the same way we did brackets. We have 2, 8, 8, whatever 36 minus 18 is, which I think is also 18, so 2, 8, 8, 18, probably 18, 32, 32. So the outermost electron shell of an atom has up to 2 or 8 or 8 or 18 or 18 or 36 or 36 electrons. I think that's true, and we're going to go to the next slide and see if I wrote that down correctly. Dang it, it was 32. Are those 32 apart? Yes, they are. I don't know why I was saying 36. So, the maximum number of electrons in the outermost shell of an atom, depending on how many shells it has. If it has 1 shell, there's 2. If it has 2 shells, 8, 3, 8, 4, 18. Okay, so here are, I called this E's for the number of electrons, and let's go ahead and copy E's over into our command line. There we go, E's, there it is, looks great. Okay, let's go ahead and plot that. Okay, so I'm going to plot it. Creating a naive, that is specifying no options. Plot is very easy. Okay, so I have PLT, which I already imported. I'm going to type plot, and I'm going to type E's, okay? And that did not show a plot. Maybe it will show a plot on your computer. I don't know for sure. You can try a few things. The most obvious thing to try is plt.show.
Doesn't do anything.
Okay, no problem. You did plot E's first, right?
Oh, no.
Okay. I'll do it again. plt.plot-ease, plt.show.
Yeah, so
Okay. And then there's other ways to do this. Let's put a pin in it here. Is Taco Bell okay for you? We can also do Chipotle. Do you have a preference between those two?
this one.
Okay, cool. I don't want to starve you any longer. We are on slide 12 of 18. That's easy to remember. I'll actually just suspend this rather than powering down. No, I won't. I have to stop streaming. I'm going to pack up, and you can pack up too, and then you're welcome to join me for lunch if you want to come along.
Yes.
Is that